Okay. So, we've had this long history of mapping Mars, going back to the early days of the telescopic observations. Here is a map by Proctor, an English observer, which predates Schiaparelli and Lowell by a half a century, maybe. And again, looking through the telescope, seeing light areas and dark areas, and trying to make some sense of it. And the only way they really kind of made sense of it was by drawing an analogy to the Earth. So what would be the analogy? How would that analogical reasoning go? What do we know about the Earth that we can apply to light and dark spaces on Mars? Okay. If we imagine looking at the Earth from space, we know that we're going to have light spots and dark spots if we viewed the Earth from space. And in general, the darker areas would be the oceans, and the lighter areas would be the continents, the land surfaces. Okay. So that's taking what we know about Earth, using it as an analogy to help us interpret these observations of Mars. And so you can see that Proctor recognized his colleague Dawes by naming a continent after Dawes. So here's the Dawes continent, and here's the Maedler continent. Maedler was another important observer of Mars during this period, a German observer. And here's the Dawes Ocean, this dark area. So we're thinking of these light and dark areas on Mars in terms of what we know, which is light and dark areas on the Earth being land and water. So, to some extent it makes sense, but we know now that it's wrong. And again, we've got the South Polar ice cap at the north, at the top of the map, and the North Polar ice cap at the bottom of the map. And what's the reason for that? Okay, when you're looking through a telescope, it's going to invert the image. Okay, here's Schiaparelli's map. We've already, dealt with this already. One of the early proponents of canaling. Of course, here's Percival Lowell's map where the canals become very, very straight and regular structures. It's hard to look at this kind of a map of Mars and not think artificial construction of these structures. So this is about the best view of Mars from ground-based telescopes before the space age. And again, it's all about these albedo features. Pretty much what you can recognize is where are the light areas, where are the dark areas. Now, at this point, we're not really thinking that the dark areas are oceans anymore, and the light areas are continents. But this is the data set that's really available before we start sending spacecraft to Mars, in terms of mapping Mars. This is a more realistic map of Mars. This is essentially surface images taken from orbit, stitched together and kind of smoothed together. What we see here is the whole planetary surface. So Mars, of course, is a globe like the Earth is a globe. And to make a map, you always have to transfer that three-dimensional structure into a two-dimensional figure in some way. So in this case, think about the globe being slit in the back and Mars just kind of squashed down flat. So this represents, here's 0 degrees of longitude. This would be the Western Hemisphere. This would be the eastern hemisphere. And so that's Mars. What can you pick out from this map to be the interesting features on Mars?
The volcanoes.
Okay, we can still see these volcanoes. And here again is Olympus Mons. These three volcanoes that are lined up in a row here are the Tharsis Montes, the mountains of the Tharsis region. So here is Tharsis. That middle volcano is pretty much right on the equator. Would be a nice place to put a space elevator, but we'll talk about that later maybe. What else can you see?
Mirrored on the other side of the map, like the three volcanoes are kind of like mirrored by those three other structures on the side.
You talking about these?
Yeah.
Okay, yeah, so we've got another volcanic province here. This area is Elysium, which is another place where these volcanoes had been erupting in the past, building up these structures. What else can you see?
Ice or snow.
Okay, so we've got the polar caps. In this reconstruction, in these images, it looks like maybe the North Polar Cap is a little bit broader, but we know that the polar caps will change from season to season. Both of them have a permanent polar cap and then a seasonal cap that is mostly carbon dioxide that vaporizes in the summer months for each hemisphere and then condenses back into ice and when winter comes back to the northern or southern hemisphere. I guess one point I'm trying to get across here is that without any oceans to provide any kind of organizing structure, it's a lot more difficult to think about organizing the geography of this place. Right? You look at the Earth, a global view of the Earth, what do you notice right away? Oceans and continents, right? And so we can specify, okay, well, here's North America. We've got this piece of land jutting up out of the ocean, and we'll call that North America. We'll call that South America. We've got Africa. Okay. Without any kind of oceans on here, we've got just one kind of continuous surface. And so to some extent, it makes it a little bit more difficult to kind of organize a geography of this place. There are some other features you can point out. What does this look like here? Okay, is it a bulge? What can you actually observe about that area?
It looks a little more empty than this one. It doesn't have many craters.
Okay. That kind of borders somewhere between an observation and an interpretation. A straight observation is with a lighter colored surface. Okay. So I guess one point I'm going to try to make at this point is that when you are looking at these images, you have to figure out what can I actually see and what interpretation do I make of what I see. Now, to interpret this as a bulge, just based on differences in lighting, we might have to make some assumptions about what direction the light's coming in, whether that would indicate that this is a surface sticking up or something coming in. But there's something going on there. There is perhaps something going on here. There's this big scar running across the planet. That's that Valles Marineris canyon complex that we mentioned earlier. Okay. So this is one kind of a map. It's just kind of a digital image mosaic map. It has certain data, information that it presents to you. There are things you can interpret from it. What I want to do is spend a little bit of time looking at some different kind of maps. So here's another map. This is a shaded relief and surface coloration map. So if you, let's see, can I? We zoom in here and look at Olympus Mons. How is the shaded relief handled?
It's kind of like a bevel effect.
Yeah.
Describe what you mean by the bevel effect.
Bevel effect has it shows that it's elevated based on the shadow underneath and the highlight over.
Okay. Yeah, so we see there's, oops, let's go back to a pencil. We see shadowing on this side, and I don't have a white pen, so let me just use the laser pointer. We see this surface being highlighted. Clearly, we've got the situation where the map makers are, having the lighting direction coming in from this way. This makes it much easier for us to interpret that this is actually a huge bulge coming out of the planet. This would be Olympus Mons, 21 kilometers above the surrounding surface. So that is huge. If we look at Valles Marineris, we can again use that shaded relief to make it a lot easier to interpret the topography of some of these structures. Let's go back and look at that Hellas Basin area. Does it look like a bulge? No, it's not. It's not shaded in the same way that Olympus Mons is. So it's clearly not a bulge. We've got those Elysium volcanoes that we mentioned before. Elysium Mons. Mons just means volcano. Tholus is another word. Basically, we've got a lot of landforms that are either sticking up out of the planet. They're either mountains or Mons or Tholus or Patera. These are conical volcanic structures sticking up. What else can we see? Okay. We've got relatively smoother surface in the north, and as we go to the south, it gets more and more cratered. Okay, that would be an observation. Fewer craters in the northern hemisphere, more craters in the southern hemisphere. What would your interpretation be?
Southern hemisphere is older.
Southern hemisphere older, been around longer, been whacked from space more often than the northern hemisphere, which is younger. Something has happened in the northern hemisphere to wipe out older craters, and this is a younger surface that has not had as much time to pick up impacts from space. Okay. So here's another map. This is a topographic map. How many of you hike? Okay. How many of you use topo maps? Topographic maps basically are showing what? Elevation. Okay. So we've got this elevation scale over here. We have high elevations in the lighter tan colors, and we've got the lower elevations in these darker more bluish tinge. There is there's no sea level on Mars, right? Because there's no sea. We measure a lot of elevations against sea level, right? We have no sea level to measure elevations against. So what we have on Mars is called the mean datum. Basically the middle data point on the elevations. And these map makers have decided to use one color scheme for everything above that mean elevation and a different color scheme for everything below. So now, does it become easier to interpret what's going on with Hellas Basin? Clearly not a bulge. It is the biggest. Let me be careful how I phrase that. It is the most obvious, largest impact structure. It's in the southern hemisphere of the eastern side of the planet. Here, Argyre Basin, another large impact basin. We looked at Isidris Planitia earlier. That's another one of these large impact basins. Okay. Now I want to talk just a couple of minutes about the color scheme here. If you look at that map with browns and blues, what interpretation might be in the back of your mind based on the color scheme?
Land and water.
Land and water. Okay. We know there are no oceans on Mars. It's a question whether or not there was ever an ocean in the past. I think I just want to raise a cautionary flag here. You have to be very careful. You know, you show this kind of a map of Mars to people over and over again, makes it very easy for them to think of, oh well, it must have been an ocean in that area in the past. There is no such thing as a neutral map. You know, all maps are making points. All maps are making interpretations, even when you get down to something like the color scheme here. So, I mean, it could as easily have been that the elevation scale was reversed. It still would have provided the same information about elevations. But in some respects, based on our experience here on Earth, this feels like a more natural color scheme. But it also, you have to be careful that it doesn't necessarily bias our interpretation. And then one final map. You'll see a lot. Is this psychedelic color scheme of data? This is basically not a plot of any kind of photographic observation of the planet. Clearly, we don't have Technicolor Mars out there. This is a representation of data, of elevation data. So the Mars Orbiter Laser Altimeter, which is what MOLA stands for, is was an instrument that was on the Mars Global Surveyor. And that's what this is all about. So how are we doing on time?
We have like 10 minutes.
Okay, perfect. So in this case, we're basically what is being plotted here in the form of a map on a globe is essentially, I think, millions of data points. Okay, the Mars Global Surveyor mission was orbiting around Mars in a polar orbit so that it could cover the whole planet. And while it was doing that, it was constantly beaming down laser pulses from orbit, measuring how long it took those laser pulses to bounce back, and using that data to calculate point by point by point on the planet what elevation those different points were. And then when you assemble them all together into a globe here, you can see very clearly these elevation differences. So again, what are the major features that we see? Many of the same ones we've been looking at, because many of those features are correlated with elevation. What are, yeah, I got a pencil. What's going on over here? Volcanoes. There are volcanoes in the eastern hemisphere. So which volcanoes? Elysium. Okay. So this is the Elysium volcanic province. Okay. This structure here, Hellas Basin. This structure peeking over the edge is Argyre Basin. What's this guy? Olympus Mons. We've got Arcea, Pavonis, and Ascrius Mons, the three huge volcanoes in the Tharsis region. This is Alba Patera. Not as tall as the other ones, but what do you notice about the size of it?
Wider.
It's much wider. Okay, it's a much shallower shield volcano. If you take a look at the actual mass of material that was erupted in Alba Patera, it's actually larger than these Tharsis Montes volcanoes that are sticking up higher. You can clearly see the crack in the planet that is Valles Marineris. See all of this kind of chaotic, broken up area here. That's that chaotic terrain. That Mariner 6 or Mariner 7. One of those pair happened to come across and catch part of that. Just by luck, the track of, let's see, is that right? You know, just by luck or bad luck, the track for Mariner 4, 6, and 7 all went across pretty much heavily cratered southern highland terrain, which is why they got so many pictures of heavily cratered, ancient-looking landforms. Okay. So I guess that would be kind of a basic orientation to Mars, the planet. Looking at these features, the kinds of topography and so forth that you can see on the planet, what would be the questions that would come to mind? What questions come out of these observations? What are the striking features that you see here?
The way that you said before about how like you would assume that there used to be an ocean there, like it really makes you wonder why the whole northern hemisphere is so much shallower than us.
What's going on? I mean,
Or it's smoother and
Yeah.
younger. Like, why?
it is smoother and it is kilometers lower than the southern hemisphere. That you know, this is probably the most striking feature of Mars, the planet. I mean, if you look at the Earth, you don't have all of the continents, you know, on one side and a big depression on the other side. So how do we explain this? What are the possible explanations for this major difference between the northern and southern hemisphere? You know, why do we have old cratered southern highlands and younger smoother northern lowlands? That's a pretty fundamental question of Mars geology. What other questions come to mind?
This is random, but where did all the rovers go, like Spirit and